Hello there. Today, DeepMind published a new paper called AlphaTensor. This is a system that speeds up matrix multiplications of all things. Now, I know it sounds a bit boring to speed up matrix multiplications. That's like not as flashy as some of the other things DeepMind has done. But since matrix multiplications are at the foundation of pretty much all of science, a speed up of 10%, 20%, or even 1% in this domain is huge and can make the whole world better off. And this is really cool because it also shows how DeepMind took their original ideas from something like AlphaGo and pulled them through all the way to now where they have real applications in science. And that's cool. And it's a bit a validation of this idea, because a lot of people said initially when DeepMind focused that much on games and things like this that it's just for press, it's just flashy, and to a certain degree it is, but definitely it is also applicable because you can frame a lot of things as games, not just Atari and chess and Go. In fact, matrix multiplication, as we'll see, can be framed as a single-player game, essentially, called TensorGame. And then you can apply much the same techniques to it as you do solving chess or solving Go. So we're going to look at this paper. As I said, this was published by DeepMind. It was published in the Journal of Nature. And yeah, it's a big deal. I think it's a big deal. And yeah, let's dive in. We're going to look at what the problem actually is, how it works, and what the actual results are. Hi, this video is sponsored by Assembly AI. Assembly AI does real-time and batch audio transcription of audio and video files, powered by the latest advances in artificial intelligence. So if you are a developer or work for a company that's looking to get more out of your audio or video data through transcription and audio intelligence, Assembly AI is the best place to go. Not only do they have a user interface where you can just upload stuff, but they do have a very powerful API. But transcription isn't all they do. Once your audio is described, they actually post-process it in many different optional ways. So they can do things like speaker classification or annotations of various forms inside of your audio. One feature I'd like to particularly highlight today is the sentiment analysis. Now, we're all familiar with sentiment analysis, but have you ever done it on a piece of transcribed audio? Not only can you infer it from the text, but you can actually infer it from the tones of voices, the breaks people take, and much more. In order to use this feature with Assembly AI, simply provide the sentiment analysis equals true in your request, and Assembly AI will do the rest for you. You'll get the result as a neat JSON output, and you can take it from there. So if you're interested, head on over to Assembly AI, use the link in the description to let them know that I sent you. They're the single API to transcribe and understand audio. They do so in batch and in real time via WebSocket. They accept all kinds of audio and video formats, and they do so in over 15 languages. Give it a try, and thank you very much to Assembly AI for sponsoring this video. And now let's get into the video. So the paper is called Discovering Faster Matrix Multiplication Algorithms with Reinforcement Learning. As I already said, if you don't know what matrix multiplication is, we not go too much into this here. Suffice to say, a matrix is just kind of like a bunch of numbers, and there's a specific way of multiplying these bunch of numbers with a bunch of other numbers, and you get a bunch of other numbers. So essentially a matrix is a square box of numbers, and we have ways of multiplying them. And that's all of science. There you go. So what's the actual deal? So if we go through it, and I'm going to make this a tiny bit bigger right here. So if we have a matrix like A1, how they call it, A2, A3, A4, and we multiply that by a matrix B, B1, B2, B3, B4, right? The classic algorithm of doing matrix multiplication goes something like this. If I want to have the entry up here, then I look at the row, I take that row of this matrix, I look at the column, I take the column of this matrix, I compute the inner product. So that's kind of like A1, B1 plus A2, B2, right? That's the thing. And I do it for every single component right here. So A1, B1 plus A2, no, B3 is that. You see I already fail. So I do that, and then I compute this one by using this row and this column and so on. And you can see there's a bunch of stuff coming together, mainly additions and multiplications. So we have an addition right here, and we have the multiplications obviously in between the components. Now, it just turns out that on our hardware that we use in silicon, addition is much, much faster than multiplication. So the bulk of the time that a processor is going to spend on doing matrix multiplications is actually doing the individual multiplications between the numbers. The additions are not the issue. So the question is, how many multiplications do we need in order to multiply two matrices? Now, it's sort of the classic algorithm. If I have matrices of size n by n, then I'm going to need about n to the third, I think, multiplications of achieving that. So I need to do every row with every column, and each of those inner products is again of size n, right? So those are my the square is everything with everything, and then inside of each of these of the inner products, I again have n multiplications. Now, what is already astounding is that, because you would think this is right, I need this, I need to do all of these multiplications to compute all of these numbers. Like, I have no choice. If I want to compute these numbers, somewhere there needs to be a multiplication between this number and this number and this number. This, and you see I'm terrible at this. So between this number and this number, and between this number and this number. And that's naturally two multiplications. I can't get around it. And so I need to compute two multiplications for each of the four entries right here. That's 2 to the third, that's 8. And I can tell you it's faster than that. There is a way of doing it faster. In fact, it's displayed right here. So you can see, I hope you can see, it's not all too big, but if you compute this term right here, M1 is A1 plus A4 times B1 plus B4. So I would first go, do I have another color? Yes. I would first go and add those two numbers, and then I would add those two numbers, no multiplication yet, and then I would simply multiply the addition of the two numbers. That's just one multiplication between two numbers, right? Not an inner product or anything. So that's a term that I'll call M1. And then I do this a bunch of other times. You can see here, it gets kind of tricky. You subtract. Subtraction is essentially addition as well, so it's really cheap. But each of these terms right here is just one scalar multiplication. And then from these intermediate terms, I can compute down here, you can see again, only additions, the final product. And if you calculate this all out, you'll actually see, yes, it actually works. It works out. We can try to follow one of these things. And oh yeah, the catch is there's only 7. There's only 7 one of these multiplications. And that seems like magic, right? It seems like it shouldn't be possible. But I'm going to convince you that it is with a simple example. In fact, you already know this. If you, for example, take the following. So take a squared minus b squared. Right? This is a very common formula in sort of high school algebra. So that is a times a minus b times b. Two multiplications, right? One multiplication here, one multiplication here. Now, I can rewrite this, as you know, to a plus b times a minus b. And look at that. There's now just one multiplication. That's literally it. But you might say, well, it's still the same thing. Yes, what you're doing is you're trading off addition for multiplication. In fact, when you calculate this out, as you know, this is a squared plus ab minus ab minus b squared. right? And then these terms here cancel out. So in fact, hidden in all of this are 1, 2, 3, 4 multiplications. However, by clever arrangement, it's actually the 2 multiplications that we started with out here. So by cleverly arranging things, right? You and then later, so this would be the intermediate term 1, I guess they call that M1. This would be the intermediate term M2. By cleverly arranging these intermediate terms so that later multiplying them actually cancels out some of the terms, you can have it such that one scalar multiplication with more additions than you would usually do, in fact, results in the same result as 4 or respectively 2 multiplications if you cross out the canceling terms, but with fewer additions. And that's exactly what we want. So you know this here already, and the same principle carries over to the matrix world. In fact, when you look at one of these entries, we can quickly look at one. Let's look at C2 right here. So C2 is M3 plus M5. Well, what's M3? M3 is this one right here, plus M5. Well, you already see. What's C2? C2 is here, so that's this row times this column. So we need an A1 plus A1 B2 in there somehow. So A1 is here times B2, that's this term. And we also need an A2 B4. Well, A2 and B4 and A2, that's here. And now all we need is that the other terms cancel. Well, there is a B4 times A1, and look, there is an A1 times B4 with a minus sign. They cancel. So that's the general principle of why it is possible, the seemingly impossible task of speeding up matrix multiplication, why it is possible. And again, the speed up isn't because of some math magic. The speed up is because we only care about the number of multiplications, because our hardware is bounded by the number of multiplications, and because we can trade off multiplications for additions, right? We don't make speed appear out of nothing. We simply customize it more to our hardware. So how do we now formulate this as some sort of game, right? It seems to be that the game is to find these formulas right here, to find this algorithm. This is an algorithm. This is valid for any multiplications of 2 by 2 matrices. Any of these, you can multiply like these, it'll give you the correct result, independent of the actual coefficients. But how do we set up a system that could find this right here? If you as a human were to find this, you'd be like, let me try. Well, it turns out there's a neat formalization of finding these algorithms as a tensor decomposition. So for that, you have to look at the tensor right here. Now, I don't know if you can see this. The rendering of the PDF here is a bit small, but I'm going to try to keep it zoomed in like that. This is a 3-dimensional tensor. You might say, wait, I thought we were dealing with 2-dimensional matrices. Well, yes, but the problem of finding the algorithm of multiplying 2-dimensional matrices can actually be phrased, or let me other than that, let me say the multiplication of 2-dimensional matrices can be phrased as a 3-dimensional tensor. And then finding the algorithm is a decomposition problem of that tensor. So let me show you what I mean. Here you have that tensor. You have the matrix A unrolled here into its components. You see A1, A2, A3, A4. You have the matrix B unrolled in this dimension into its components. And in the last dimension, so this is in the last dimension, this dimension here, you have the resulting matrix unrolled. This is a matrix, this right here, it only has components 0 or 1. It has no other numbers in it. There's just either a 0 or a 1. Now, the ones you can see here colored in solid blocks. And whenever there's a 1 in this tensor, it means that that's a step you have to do. So ideally, there should be a 1 for every entry in the C dimension right here. So you can see C1. How do we do it? We go look. Aha, okay, this block here is the entry for C1. Now, what do we need to do? We look at the other dimensions. So this corresponds to B1 and A1, right? A, this is this dimension, B1 is this dimension. So this block being solid, it means in order to get C1, we need to multiply A1 and B1. Now that's not enough. There's also going to be another entry for C1, namely, as you can see down here, this is also on the dimension on the axis that corresponds to C1. And it in turn corresponds again to A1, this dimension, but B3. So we have to multiply A1 by B3 also to get C1. And if you look, C1, it's this times this. Wait, now so A1 times B1. No, it's A2. I might be confused here. Or is the drawing confused? It should be A2 multiplied by B3. Oh yes, of course. Obviously. Sorry. Yeah, this is A2. This slice here is A2. I was dumb. So it's a three-dimensional tensor. I'm not used to these kind of higher level mathematical stuff. That scares me. But you can see, using this tensor, we can fill in the blocks that we know correspond to matrix multiplication entries. And this is just a classic algorithm, right? I'm doing nothing fancy here. I'm just applying the high school matrix multiplication algorithm, saying like, okay, what do I need to get for this? I need to get these two plus these two. And for every multiplication here, I make one entry into this tensor. So at the location that I want, C1 is the result. I'm going to make one entry here for the first multiplication. I'm going to make one entry here for the second multiplication. And I'll get a tensor. Now, it turns out that a low-rank decomposition of this tensor will exactly give me an algorithm to perform this multiplication. In fact, any decomposition of this tensor will do that. So I can decompose a tensor, I can decompose a matrix, but also a tensor into individual components. Now for a matrix, you may know, for example, that if I have a matrix A, I can write it as a sum of outer products of vectors ui, vi, right? There's outer product. So every component here is going to be some sort of a vector multiplied by some sort of other vector. So the outer product will give me a matrix, but the matrix is of rank 1. And then I add many of these matrices, and I'll give me the original matrix. I can do that with any matrix, right? You might know some special cases of these decompositions. For example, spectral decomposition usually extracts also some sort of a scalar right here, and then makes these two orthogonal. So there are various ways of how to do this, but in our case, any decomposition of this matrix will give us an algorithm. And it's going to be a valid algorithm because it's a valid decomposition of the tensor. Therefore, if I apply that algorithm, I will get the correct matrix multiplication. Here on the right-hand side, you can see one such decomposition that corresponds to this algorithm right here. There can be various different algorithms, all with either the same or more or less steps, which correspond to various ways of decomposing that tensor. So the tensor specifically, you can see here matrices U, V, and W. And specifically, the decomposition goes as the matrix, how do we call that? Maybe T, they call it T. So specifically, that matrix T is going to be decomposed into individual parts of vectors ui, outer product with vi, outer product with wi. Again, I can do this in any case. These are going to be rank 1 three-dimensional tensors. If I do that, right, one vector, and one vector gives me a rank 1 three-dimensional tensor. If I add many of these, I'll get more rank more tensor. And if that addition results in this tensor right here, that means I have found a decomposition of that tensor. And this also directly corresponds to an algorithm. Let's look at that, how that works. So assume that I have such a decomposition, what I can do is I can take the first vector here and the first vector here, and that will give me kind of the components that I need to compute. So the first vector here, you can see, corresponds to A1 plus A4. So I have to take A1 and A4, the two entries with the ones. And then of the B matrix, I have to take B1 and B4, this thing right here. And I have to build this thing. So I have to multiply them. Multiply those. And that will become M1. Right? So that will result in M1. M1 I'll remember for later. So M1. Similarly, the second columns will become M2, M3, and so on. And then later, I'll go and look at my matrix W. And now I'm going to look at the rows of the matrix W. And this row tells me which one of the M terms I need to combine together. So one, well, that's actually good, better visible. 1 M1 plus 1 M4 minus 1 M5 plus 1 M7. Okay, that's exactly this row right here, which is going to give me C1 as an entry. So if I have a decomposition, I can just read off the algorithm. And just to understand like a tiny bit more what's happening right here, I also thought we'd look at the same entry we did before. So let's look at C2. How do I get C2? Well, I need M3. I wanted to do something different. Let's stay at the C1 and let's look at what that actually does, like how this outer product even looks, right? Because I still can see that maybe some people have a hard time visualizing what's happening. So I just told you how to do the algorithm, but I also showed you, well, there's this decomposition right here. And technically, that first column of all of these vectors should correspond to the first entry in that decomposition. But how does that look? Well, if I take U and V and I build the outer product, essentially what I have to do is I have to take U, and let's put U into the column here, just into the row. Let's transpose U, and I outer product it with V. So I need to take 1 times U, then 0 times U in the next column, then 0 times U in the next column, and then 1 times U in the last column. That's this, right? And now I want the outer product with W here. Okay, I'll go into the third dimension. So I take 1 time that slice that I just computed. That's my front. Then 0 times, that's like 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. And you can, like, it's a cube. You fill in the back yourself. And then I take it 1 time again. So 1, 0, 0, 1, 0, 0, 1, and so on. So that's going to be a cube with 1s at the corners. 1s, and everything else is 0. So this cube with 1s at the corners and everything else is 0 is rank 1, is a rank 1 3D tensor because it can be decomposed into the outer product of 3 vectors. Not every 3D tensor can do that. Only rank 1 3D tensors. Right? And now, if we go through all of these columns right here, we do all of that, and we add all of these cubes that we're going to get together, then we get back to this thing right here, which means that, again, it's a valid decomposition. And you can already see here, 2 of the corners are actually correct. So this corner right here, yes, we just made it, right? This corner right here is already done. It's this corner here. That we have it, right? And the corner down here, we have it too, here. So if all of this is correct, right, then it should be that in none of the other columns, we're going to modify these corners again. So let's quickly check that for the top left corner here. So the 1, 1, 1 entry. That's this, this, and this. So none of these things. So these are 1, 1, 1 here, which gives us that result. So in no other column should we get an entry here. There's always going to be 1, 0 somewhere. And you can see, right, there's a 0 here. In fact, here too. There's 1 here and here. There's 1 here. There's 1 here, 1 here, and 2 here. So good, right? This is the only place where that's modified. So that corner is this corner in the final result. However, if we look at another corner, for example, this one here, well, this one is 0 in the final tensor. But here we have it as a 1. So our hypothesis is that in some of the other columns, this must be kind of reverted, right? Much like this component right here is reverted later. Or, you know, however you want to watch it, this needs to be cancelled out somewhere. So let's go and find out where it is cancelled out. So currently, this is a 1. Why is it a 1? Well, it's a 1 because a 1 is here, a 1 is here, right? Because we're in other corner now, and a 1 is here. So dimension 1, dimension 4, dimension 1 here. Our hypothesis is that this is going to be somewhere later subtracted again. Well, okay, there's a 0 here, a 0 here, so that's not it. We have 1, -1, and 1 here, so 3 candidates. Oh no, we're in the bottom row. There is a 0 here, so not this column. There is a 1 and a 1 here. Okay, this already looks promising. Now there's a 0 here, so it's not this column. So look at this column. There is a 1. Boom. There is a 1 down here. You can't see it anymore, but it's there. And there is a -1 here. So this outer product of the last column is going to result in -1 as this corner of the cube, right? So in its cube, it's going to have a -1 here instead of a 1. And if we add those together, remember we add those all together because it's a tensor decomposition, we get 0 at this place right here. And if we now go and look, okay, into C4, this is C4, right? The last column, we should see that, no, wait. No, that's not something we can see right here. Sorry for that. In any case, I hope you can imagine a little bit in how that goes. So you build up these things, these cubes, which are low rank but quite complex, right? And you then add them together, and the correct things need to cancel out such that you get back this thing right here, because this thing actually corresponds to the original matrix-matrix multiplication. And if you find a correct decomposition, then that also corresponds to the multiplication. But the decomposition also gives you directly an algorithm to perform this multiplication, a different one than the original tensor. And now it's only, can you find a decomposition where this dimension right here is very low, right? Now we can all find decompositions where this dimension is really high, because we can just consider the individual entries of the original tensor, and for each one of them we construct such columns, right? So that it's one at exactly that place. However, if we do it in a smarter way, we can do with less columns, and thereby our decomposition has a lower rank, and thereby we need less multiplications because each column corresponds to exactly one multiplication. Okay, that was long-winded, but I hope you get a little bit of the idea of why it is even possible to speed up matrix-matrix multiplication, of how we represent a matrix-matrix multiplication as a 3D tensor, and why a decomposition of that tensor gives us a new algorithm to perform the same thing, and then that the rank of the decomposition is directly corresponding to the number of multiplications we need. So the goal is to get a low number of terms in that decomposition. So what does now, how do you do this as a game? They formulate this as, okay, this is all, we probably talked about this, yada yada. And again, this has nothing to do with what numbers are in the matrix, right? The fact that there's 0 and 1 here just corresponds to the algorithm itself. So we're working with the algorithm. We're not working with the numbers. Also, you can see there's just zeros and ones and minus ones here, but this can be, in fact, any decomposition. This can be negative 3.5, 100,000, and so on. But for simplicity and because of some symmetries, I assume, you can actually limit that. In fact, they do limit it to -2, -1, 0, 1, and 2 because of numerical stability, and because, well, I don't know, maybe there's a super smart algorithm with -3.7 as a coefficient. But in any case, they now apply AlphaZero to this. So they have a few special network architecture tricks where they exploit some properties of linear algebra. For example, they say, well, if you change the basis of a linear operation, then it's kind of still the same problem. So you can change the basis of matrices, and it still essentially represents the same transformation. However, to this algorithm, this is like a new thing, because now there's different numbers, right? The algorithm looks different because it's sort of a transformation of one another. Now, there's one class of research papers that say we're going to build our neural network to be invariant to that, but there's an entirely other class, and this one here falls under that, that says, well, great, so that's kind of like much more training data. If one training sample corresponds to like many, I can make many training samples out of one. That's free data augmentation. So they use change of basis here, which is a fundamental property or a fundamental action in linear algebra to create more training data. They also say, well, look, while decomposing a 3D tensor is really hard, constructing one is really easy. We just sample 3 vectors, we make the outer product, we do that a bunch of times, we add those things together, and we have a 3-dimensional tensor that now you can try to decompose, right? So they can also create synthetic training data. All very smart tricks in order to feed their system with more data to train on. So the system's going to be trained on exactly providing these decompositions. We'll look at how in just a bit. The last thing I want to do is the neural network architecture that they analyze things with here. It's transformer-based. Who would have thought that? Now, interestingly, they say they generalize axial attention. They have a diagram of their architecture down here. And you don't need to know yet what they do with the architecture, but essentially, this is a reinforcement learning algorithm. So the input here is the current tensor and the history of tensors, which I find really interesting, that they also consider the history of things. this goes into some sort of a torso or a body or whatnot. Then out comes some sort of embedding. This goes into a policy and a value head. You might be familiar with all of this if you're familiar with reinforcement learning. The action space here, as we've discussed, are to select three vectors, one of u, one of v, and one of w. So you select one of the columns of the thing we just saw, right? We saw there are u, v, and w, which should ultimately give you as the sum of outer products this tau right here. And an action is you provide one of these columns of each of the entries. So one column at a time. This is an action. The next step in the game would be to determine this thing. The next step would be to determine the next column. The game is over whenever the multiplication here is actually equal. So you can formulate that in a different way by saying, you can formulate this in a different way by saying, well, the tau should be the sum of ui, outer product vi, outer product wi, right? So once I have u1, w1, and v1, I can subtract that, right? So this is step one of the game. Step two would be tau minus u1, outer product v1, outer product w1, 1, not I, 1, must be equal to the sum of I equals 2 to, potentially infinity of ui. So once I have one, once I have an action, which is three vectors, I can subtract that from my original tensor. And then the goal is to find the next action to subtract from the original tensor. The game is over exactly then when this here is equal to 0, right? It can go negative in some entries, as you saw, but if all the entries of the tensor are 0, then the game is over. This is obviously a discrete problem, and it is in fact NP hard if the tensor is of an order higher than 2. So this is not an easy task, and the action space is huge, right? You don't just emit one number. You emit the three vectors, each with their respective entries. So that is a ginormous action space. It's actually a much larger action space than something like chess or Go. So that's why this problem is particularly difficult. This is a finer diagram of the architecture here of the torso. So what they do is they take the history here of the tensors that came along in the last time steps, and they project it down to this grid. You can see right here, this is S by S by TS, T being the number of steps, so TS plus 1. They project it down in various ways onto these grid layers. Then they have linear layers linear layers transforming this into some sort of c-dimensional vector. You can see here you reduce the time dimension down to the c dimension. After that, you have these, what they call attentive modes, and at the end, some sort of output. Now, the attentive modes, I hope that's this right here, policy head diagram. Oh no, the attentive modes are, as I said, they generalize a form of axial attention. And then here, the way they do the actions, as common in reinforcement learning, you take the embedding that comes out of the torso here, and this is kind of like an autoregressive language model, if you will, that outputs the next action. So here you have no action at all, and then you output a policy, and the policy is a distribution over your action space. There's also an output to the value head, and you do that. So here, next action, and so on. The value head is simply you take that embedding from the policy head, you shove it through some neural network. And you can train all of that end to end. Again, if you don't know AlphaZero or reinforcement learning in general, I have many videos on that. So the gist is that you pair this network here, which we just saw is this one in kind of finer detail. You pair this with a so-called Monte Carlo tree search. So in order to solve these games, you're in some sort of state, right? At the beginning, your matrix is full, you haven't subtracted anything, or your chessboard is at the initial state. And then you consider different moves to do. And for each move that you could do, you then, if you do it, you can consider more moves, right? Or your opponent can consider more moves. And for each of those moves, again, you consider more moves. So this is a tree search algorithm. Now, the AlphaZero style Monte Carlo tree search works in a way that the policy and value functions of your neural network, they will guide you through this tree search. So they will suggest to you nodes here that are more likely for you to be able to win the game. Again, winning in this case means getting a successful tensor decomposition. And some that are, and say, well, now this one, you shouldn't even try. You shouldn't even explore that direction. So that saves you from considering all those possibilities, narrowing it down onto just a few that you then go explore further. And you can ask your network again, well, if I were to go here, what would you do next? Well, I would maybe try this one or this one. Okay, and you only need to search those. And you iteratively train this such that once you actually play the game and you do this and you go down and at some point you finish the game, either you reach the zero tensor, which means win, reward of 1, or you don't finish the game, which is a bad, so very low reward. Then that feeds back into all of these things. So it feeds back training the neural network to make better predictions. In fact, the reward isn't just 0 or 1. They do give, and I believe they describe it somewhere. They do give a -1 reward for every step that's being done. Nope. Well, I don't exactly know where they describe that. Yes, there. So they say there's a reward of -1 for every step taken to encourage finding the shortest path. This is much better than just giving 0 or 1 reward. For one, this actually encourages a low rank decomposition. On the other hand, it also provides a denser reward signal. So you don't have to, it's not like you either win, because this problem is super difficult, right? And to stumble by chance upon this would be not really, it would be like really lucky, and the reward would be super sparse. So they say, well, you get a reward for every step taken, a negative reward, so better take fewer steps. And then on top of that, they also pair a supervised reward from this synthetic demonstrations, because in the synthetic data, not only can they generate data, they actually know the correct steps to do. So they can train the neural networks in a supervised fashion. They can say, hey, here's the situation, and we already know, because we made the problem, we already know what steps you should take. So that gets on top. Do they say that somewhere here? Maybe not. Somewhere they describe the loss in detail, where they say, well, our loss is this plus the supervised loss. In any case, that's how they do it. And the whole algorithm is essentially here. They start out with a game, which is one of the original tensors. They change the basis to make it, to augment the data, to make it into one never seen before. They do the Monte Carlo tree search to determine the first step to do. So the tree search is just kind of imaginary. You kind of think ahead. Once you know what to do, you do the step. Then you do the tree search again, and so on until you're at the end of the episode. That represents a played game. Either you win or you lose. You take your reward and you use that to train. So this is learning. You put that in your buffer of games. You also have your synthetic data right here. You sample these things. You train your neural network either from a synthetic data point or from one that you've already played in order to predict better what actions to do, which is the policy that's guiding you through the network. And also the value head, which is a function that estimates the value of each node in the network right here, also helps you to guide you. So the policy head, in fact, guides you to which path you want to go down. And then you don't always want to go down all the way. So at some point you just cut off and you ask the value head, well, how much do you think this state is worth? You aggregate that all on top and you look at the top level of all your available actions, which one looks the most promising, and that's what you go with. So that's MCTS AlphaZero style in a nutshell. The results are pretty astounding in that you can see right here for small matrix multiplications, they actually do find better algorithms. And you would think that something like multiplying 4 by 4 matrices would be kind of figured out by now, but no. The best known algorithm had a 49 multiplication decomposition, and now we have a 47 multiplication decomposition. Now this is modular, so as far as I understand, this is over a finite field. This is not real matrices, but I think for real, I'm actually not super sure. For real matrices, I believe the thing down here counts. So, for example, multiplying 3 by 4 matrices to 4 by 5 matrices, previous best known rank 48, now 47. Again, doesn't seem like much, but is. And as you go higher, this gets more drastic. Multiplying 4 by 5 to 5 by 5 matrices, there are 4 multiplications less in the algorithm that AlphaTensor found. You can see in the diagram right here, as you go up in rank, so best rank known for given problems, and here improvement in rank, how much AlphaTensor improves. You see there's a clear diagonal line, and that is maybe a bit obvious because us humans, we can't really come up with, well, give me an 800 multiplication decomposition of some tensor. It's just kind of a bit above our league. So what we do is we kind of break it down in small problems and then just kind of recursively apply these strategies. And if you can consider a problem in its entirety, then obviously you have a better chance of just, canceling out something somewhere at some point. Or, are these just the symmetric up here? Okay, that could be as well. These are the symmetric, and then these are finite versus modular versus standard versus real. Good. Well, the others can be real. I'm just going to stop talking now. Another cool thing you can do is, you may have noticed, nothing in the base algorithm actually says that, low rank is the goal. That's simply us putting this into the reward. We say, well, for every step you do, you get a negative reward. Ergo, the algorithm is encouraged to take as few steps as possible. However, we can just do something else. This is black box, right? There's nothing. The algorithm just gets this at the end, and it needs to learn this implicitly. So we can swap it out. We can say, actually, we're not that interested in lowest amount of steps. We're going to swap that out, or in this case we're going to add another reward on top of that that says, well, we modify the reward. They say right here, we provide an additional reward at the terminal state. So you only get this additional reward after you actually found the correct solution. Otherwise, it would encourage the algorithm to not find correct solutions but prioritize something else. So we give this reward once the algorithm has found the correct solution. We still retain the step reward, so it means it still needs to find that in as few steps as possible. However, equal to the negative of the runtime of the algorithm when benchmarked on a target hardware. So now they go and they take a V100 GPU or a TPU, and they say, you get additional reward if your algorithm is really fast on this particular hardware. Now, the algorithm, AlphaTensor, has no clue of what a V100 is or what happens in there. It's a complete black box to it. I think they even have a diagram right here somewhere that says black box. So, but still, through the power of reinforcement learning, the algorithm manages and says, well, there are a lot of algorithms with a low decomposition. A lot of them are kind of equivalent. There are thousands of algorithms that do, do a decomposition of this tensor, which is another thing they mention in the paper, but I'll get to that in a bit. But I'm now going to search for one that is very fast on a particular hardware. And you can see right here, if we actually take an algorithm, we tell AlphaTensor to optimize it for a TPU, then there is a significant speed up if we measure that on a TPU. Similarly, if we take one that we optimize, we tell AlphaTensor to optimize for a GPU, right? And we get a significant speed up. Not vice versa, though. Right? So you can really see the impact that this has. You can tell the algorithm to come up with a custom tailored solution. This is really cool. And I think it's, this must not stay with matrix multiplication, right? You can think of compilers working in exactly this way. Right now, compilers have heuristics and rules of how they transform source code, but essentially, as long as you can prove that you're still doing the same, or I guess kind of the same, you could use these very same techniques in order to come up with a program with a compile arrangement that optimizes for a particular hardware for a particular metric, memory, speed, cycles, whatnot. So there's so many applications of this, even beyond the many applications that matrix multiplication already has. And if you thought, well, in practice we have much bigger tensors even than 200 dimensional and so on, and there's got to be some limit to the algorithm at some point because this seems compute intense, then yes. However, even like something small like this algorithm here, we can recursively apply it to get speed up even at higher dimensions. So that's pretty cool too. It's not going to be the most optimal algorithm, but it's going to be a more optimal algorithm than we already have. So this will help at any size. Yeah, lastly, what I want to mention is briefly that they also say that it doesn't only help practically, it also helps a lot the sort of mathematical view that we have of matrix decompositions, because it finds like, for example, if you consider T4, which multiplies two 4x4 matrices, AlphaTensor finds more than 14,000 non-equivalent factorizations. So this means these are all different algorithms that you can use to find, to achieve the goal of multiplying 4x4 matrices to each other. And they're different. They're not just like symmetric transformations of each other. And that will, I think, that is a great benefit to mathematicians who care about complexity theory and things like this. All right, so that is about all I had to say about this paper. So to summarize, they built this game, and the same agent, by the way, plays all of these games. So the same agent trains to multiply 4x3 matrices, 5x5 matrices, and so on. There's significant transfer learning happening. So they train one agent that does nothing else but start out with a problem like this, augment it a little bit, and then try to find a decomposition. It may fail, it may succeed, it learns from it, it tries again, finds a decomposition. Does nothing to that. That's a single player game. And if you get good at the game, you can find good decompositions which correspond to algorithms to multiply two matrices. If you take very few steps in doing so, That means every step corresponds to one multiplication in the resulting algorithm. So if you're very good at it, your algorithms will have very few steps, and therefore our hardware will be able to compute it more quickly because they have to do less of the expensive operation that is multiplication. All right, that was it from me. Let me know what you think. There's more to this paper. I invite you to read it. I hope I got the gist of it across. Bye-bye.